Dear students, welcome. Today I am going to start hydrostatics and I will have to complete the hydrostatics within a very short period of time. Therefore, the classes will be examination oriented. Without wasting time, let us start. I will give you some definitions regarding hydrostatics, definitions of hydrostatics. Just the first which some definitions. Fluid. What is called fluid? Fluids are the substances which are capable of flowing. Fluids. The definition is fluids are the substances. Which are capable of flowing. Fluids are the substances which are capable of flowing. There are two kinds of fluids. Number one, liquid, and number two, gas. Gases. Liquids are not compressible. Or lightly compressible. It is highly compressible. For example, water is a liquid, and here air gas. For example, water liquid, and for example here air gas. Liquids and gas. Next, pressure. What is pressure? Force per unit area. Pressure, this is equal to force per unit area. Pressure equal to force per area. Pressure, this is equal to force per area. Just remember this. And perhaps you know what is pressure. And density. Density means mass per unit volume. Density is generally, we denote density by this symbol rho, and mass is equal to, suppose this is m. Mass is m and volume is v. Therefore, mass equal to density into volume. Therefore, if m is the mass, rho and v, suppose v is the volume. Volume is denoted by v. M equal to rho into v. Weight, W equal to weight of a body. And W equal to mg. Mass into acceleration due to gravity. This is, therefore, what is m? M equal to rho into v. Rho into v into z. Therefore, weight of a body will be equal to rho into v into z. Now, I am going to start the first chapter. Pressure on heavy fluid. Pressure on heavy fluids. There are 7 theorems on this chapter. First, theorem number 1. In a fluid at rest under gravity, under gravity. In a fluid at rest under gravity, the pressures at all points in the same horizontal plane are the same. In a fluid at rest under gravity, the pressure at all points in the same horizontal plane are the same. Now, let A and B be 2 points in the fluid. Let A and B be 2 points in the fluid in the same horizontal plane. In the same horizontal plane. Let A and B be 2 points in the fluid in the same of be 2 points of the fluid or in the fluid in the same horizontal plane. Now, case 1, when A and B can be joined, without passing out of the fluid region. Passing out of the fluid region. When A and B can be joined without passing out of the fluid. Suppose A and B are 2 points. In the fluid, A and B are 2 points in the same horizontal plane within the fluid. Now, taking AB as axis, we construct a cylinder. Construct a cylinder of small cross section A. Taking AB as axis, construct a cylinder of small cross section A. Here, fluids are there. Suppose pressure at A, this is equal to suppose P1. Pressure at B equal to P2. Pressure at A, P1, pressure at B equal to P2. Weight W will act vertically downwards. Also, the forces thrust on the curved surfaces will be acting perpendicular to the cylinder. Now, what we will do? Taking AB as axis, we construct a cylinder of small cross section A. Now, the fluid within the cylinder will be at rest under the action of the forces. Just I will write it. First, write it. Taking AB as axis, we construct a cylinder. Of small cross section. Taking AB as axis, we construct a cylinder of small cross section A. Small cross section. Let P1 and P2 be the pressures at A and B respectively. P1 and P2 are the pressures at A and B respectively. Now, the fluid within the cylinder will be at rest under the action of the following process. Now the fluid within the cylinder will be at rest under the action of the following forces. Number 1, cross section is A. Pressure at A is P1. The thrust P1A. Thrust P1A at A or acting at A. You may write here acting at A along A. The thrust P1A at A along A. Number 2, the thrust P2A at B along BA. And number 3, the wave, it will definitely pass through the center of gravity. The wave W of the fluid passing through the center of gravity Z, passing through Z, the center of gravity Z, passing through Z, center of gravity Z, passing through Z, perpendicular to AB. Perpendicular to AB. The wave W of the fluid passing through the center of gravity, and it will be perpendicular to AB. Number 4, the thrust on the curved surfaces. The thrust on the curved surfaces. Perpendicular to AB. The thrust on the curved surface perpendicular to AB. Now resolving the forces. The forces along AB we get. Resolving the forces along AB we get. Resolving the forces along AB. Now the thrust P1A along AB, it will be P1A. P2A along BA, it will be minus P2A. And the weight is acting perpendicular to AB. Weight is acting perpendicular to AB. Not only that, the thrust on the curved surfaces are also perpendicular to AB. Since we are resolving the forces along AB, therefore no contribution of the weight and the thrust on the curved surfaces. This will be equal to 0. This means P1 equal to P2. This means pressure at A equal to pressure at B. Pressure at A equal to pressure at B. Thus you see the pressure at A equal to pressure at B. This means that the pressure at any 2 points in the same horizontal plane are the same. Now, case 2. When A and B cannot be joined, without passing out of the fluid region, without passing out, cannot be drained without passing out of the fluid recipient. Now, suppose this one. A and B are 2 points. Without false passing out of the fluid. Let C and D, case 2, let C and D are 2 points. Are 2 points in the fluid. Such that the line AC, CD and DA lie entirely or wholly or entirely in the same horizontal plane. Entirely in the fluid. Now pressure at A. Now by case 1, in the fluid, in the same horizontal plane. C and D are 2 points in the fluid such that the lines AC, CD and DA lie wholly or in the fluid in the same horizontal. Now, by case 1, pressure at A equal to pressure at C. This is equal to pressure at D equal to pressure at B. That is pressure at A equal to pressure at B. That is pressure at A equal to pressure at A equal to pressure at B. If A and B cannot be joined without passing out of the fluid region, then in that case also the pressure at A equal to pressure at B in the same horizontal plane. The pressure in the same horizontal plane are the same. Next, I am going to derive the second theorem. You should remember this theorem always. Number 2. Theorem number 2. In a homogeneous fluid, at rest under gravity, at rest under gravity, the pressure P the point in the fluid which is at a depth h below the effective surface is given by, in a homogeneous fluid at rest under gravity, the pressure P at the point in the fluid which is at the depth h below the effective surface is given by P equal to pi plus h rho g, where rho is the density of the homogeneous fluid. Rho is the density of the homogeneous fluid. and pi is the atmospheric pressure. And pi is the atmospheric pressure. This is the theorem. You should remember this theorem. P equal to pi. Pi is the atmospheric pressure. Rho is the density of the homogeneous fluid. The fluid is at rest under gravity, and H is the depth of a point within the fluid below the effective surface. From the effective surface, the depth is H. Then the pressure will be equal to pi plus H rho g. This is the statement of the theorem. Now I am going to prove this. I am going to prove this. Suppose A is a point in the fluid. It is at a depth h below the effective surface. Just draw a line AB. Draw a line AB to meet the effective surface at B. Now, taking AB as axis, we construct a cylinder of small cross section. This is the effective surface. Small cross section A. Now, P is the pressure at A. Suppose P is the pressure at A. This is the P is the pressure at A. And H is the depth of A below the effective surface. Now, let us write this one. Let A be a point of the fluid. Let A be a point of the fluid which is at a depth h. Here are all fluids at the depth h below the effective surface. Now we draw a line. We draw a vertical line. AB to meet the effective surface at B. We draw a vertical line AB to meet the effective surface at B. Now, taking AB as axis, we construct a cylinder of small cross section A. Now, taking AB as axis, we construct a cylinder of small cross section A. Now, taking AB as axis, we construct a cylinder of small cross section A. Now the fluid. Suppose P is the pressure at A. Suppose that P is the pressure at A. Suppose that P is the pressure at A. Also, pi is the atmospheric pressure at B. Now, the fluid within the cylinder. Now, the fluid within the cylinder is at rest under the action of the following forces. Now the fluid within the cylinder is at rest under the action of the following forces. Number 1, the thrust PE. Thrust here, cross section is A, pressure is P, the thrust PE. Thrust PE at A, along M. Number 2, the thrust pi A, pi is the atmospheric pressure, pi A at B, acting along B. Also, thrust on the curved surfaces will be acting perpendicular to the cylinder, AB, perpendicular to AB. Number 3, the weight within the cylinder, weight W. The weight W within the cylinder W. What is weight? Equal to mass into G, M into G. Suppose this is G. Into mass. Mass equal to density into volume. Density. What is the volume of the cylinder? Height is H and the cross section is A. AH rho G. The weight W equal to AH rho G, acting vertically downwards through G. You may write through G. Acting vertically downwards. Acting vertically downwards means acting along AB. Along BA, not AB, it is acting along BA. The weight W will be equal to mass in W equal to M into G. This is G, mass equal to density into volume. Just write density. Volume is equal to the height H into the cross section A into H. Acting along B. Number 4, the thrust on the curved surfaces. The thrust on the curved surface acting perpendicular to AB. Acting perpendicular to AB. Acting perpendicular to AB. Thrust on the curved surface acting perpendicular to AB. Perpendicular. Now, resolving the forces. The forces along AB we get. Along AB. The thrust is here PA. And the pi A is acting along BA. Also the weight is acting vertically downwards. Therefore it will be minus pi A. Minus W means AH rho Z. This is equal to 0. AA will be cancelled. Therefore you will get P minus pi minus H rho Z equal to 0. This means P equal to pi plus H rho Z. You should remember this. The pressure is given by pi plus H rho Z. If there is no atmospheric pressure, then the pressure will be equal to H rho Z. If there is no atmospheric pressure, then pressure at A is given by pressure at A is given by P equal to H rho Z. Pressure at A is given by P equal to H rho Z. H rho Z. If there is no hydrostatics. Just remember this. It will be applied. This theorem will be applied in all problems, in many problems of the hydrostatics. You should remember this one. H rho Z. Pressure at the point is H rho Z. What is H? Depth of the point below the effective surface. Rho is density of the homogeneous fluid. And Z is now theorem number 3. Theorem number 3. In a homogeneous fluid, at rest under gravity, the difference of pressure between 2 points is proportional to the difference of their depths. Proportional to the difference of their depths. In a homogeneous fluid at rest under gravity, the difference of pressure between 2 points is proportional to the difference of their depths. Suppose A and B are 2 points in the fluid. At the depth H1 and H2 below the effective surface. H1 and H2 below the effective surface. And C and D are 2 points in the effective surface. Let A and B be 2 points in the fluid which are at rest. Be 2 points in the fluid which are at rest. Be 2 points which are at a depth. At depth H1 and H2 respectively below the effective surface. A and B be 2 points in the fluid which are at depths H1 and H2 below the effective surface. Let rho be the density of the homogeneous fluid. Let rho be the density of the homogeneous fluid. Rho be the density of the homogeneous fluid. Let PA and PB, let P1 and P2 be the pressures at A and B respectively. Let P1 and P2 be the pressures at the A and B respectively. Therefore, P1 will be equal to, from the last theorem, P1 will be equal to pi plus H1 rho Z, and P2 will be equal to pi plus H2 rho Z by the above theorem. From this, you will get P2 minus P1 equal to pi by will be cancelled, H2 minus H1 into rho Z. Rho and Z are constant. Rho is the density of the homogeneous fluid. Homogeneous fluid means the density is constant. Density is constant, therefore, and Z is also constant. This is constant, therefore, you will get P2 minus P1 is proportional to H2 minus H1. P2 minus P1 equal to A is proportional to H2 minus H1. Difference of the pressures, difference of their pressures, it is P2. Difference of their pressures, P2 minus P1. This is proportional to the difference of their gaps, H2 minus H1. P2 minus P1 is proportional to H2 minus H1. H2 minus H1. This is the proof of the theory. Dear students, it is very difficult to upload a long video. Therefore, after uploading this, I am coming again to discuss the remaining part of this chapter. 4 theorems will have to be given after this, and then we shall solve 7 to 10 problems of this chapter. After that, we shall start a new chapter. Today, I am going to stop here. Thanks for watching the class. Thank you.